Yes, sir.
Okay. Yes, sir. So in our last class, we have started discussion on AdaBoost classifier. And today I want to continue the same lecture on AdaBoost, designing the AdaBoost classifier. So as far I can remember, we have discussed this algorithm of AdaBoost, and we have finished the discussion on this, that is the algorithm discussion. Now in this lecture, I want to show the example with a data set for the AdaBoost classification. Let's say we have a data set that is given data set. This is a given data set. This data set is called the play tennis data set. Okay, that means we have a record of the playing tennis, and we have a record of the weather factors. So that means based on the weather factor, whether there will be any tennis match or not, we want to predict that. So that's the data set here. The data set, in this data set, we have the record of 14 days data. I can say 14 days record. And on the first day outlook, it was sunny and temperature, it was hot, humidity high, and wind that is weak. On that day, there was no tennis match. And day two, another day, we can say outlook sunny, temperature hot, humidity high, and wind strong. On that day, we also didn't play tennis. Okay, we didn't play the tennis on that day also. Similarly, day three, we can see overcast, temperature hot, humidity high, and wind weak. On that day, we played the tennis match. Okay, so in this way, we can see we have like 14 days data, and the 14 days data we have, and we want to use this 14 days data for uh, training the AdaBoost classifier. So that means this classifier we have, and we want to use this data set for the training purpose of AdaBoost classifier. But how to do that? We already know this algorithm, and in this algorithm you can see that the first step is the initialization step. So we have to initialize each and every instance, that is where I equal 1 to n, and the initialize, we have to initialize with 1 by n, that is we have to assign the weight of each and every instances just 1 by capital N. Then we need to find out the capital N in our data set. Like in this case, we have 14 days data. So the capital N is 14. Capital N here is 14. So as the capital N is 14, we have to initialize each and every instance by 1 by capital N. That is 1 by 14. 1 by 14. So now we can see it here. The sample weights, that means each and every instance weights, we have assigned the weight 1 by 14. Next one is 1 by 14. In this way, last one is also 1 by 14. Okay, so that means we have initialized each and every instance's weight just 1 by 14. Then what's next? The next is, here's the for loop. In our last class we have discussed it, and we can see that there is how many how many storms we want to construct. That is our capital M, capital M. And we can see this is a small m, the control variable, and it will start from the 1. It means we want to construct the first storm. I think no need to discuss about what is a storm, because in our last class we have already discussed it. That is what is a storm. Now we can see a fit classifier. It means we have to develop a classifier that is called a stump, weak classifier stump. We have to develop the stump g of m of x. So g of m of x means g of 1. In our case, this is the first stump, and we will pass the x. X means our data set there. Okay, we will pass the data set there. Specifically the feature vector of the data set. Okay, x, just only the x. And what it will return? It will return either negative or maybe positive. And we will utilize the weights also. Okay, so fit classifier, that means we need to develop a classifier, and that is weak classifier. So how can we develop a weak classifier? The weak classifier means it will just only have one node and then corresponding leaves. Okay, corresponding leaves. So weak classifier means we will have just only one node and their leaves. Okay, and their leaves. So that means it's kind of the decision tree, or we can say we need to find out the root of the decision tree. Like here, this is the root. Okay, then what will be in the loop? Sorry, in the root of our stump. We need to find out that. So we already discussed about the decision tree construction in random forest, and on that case we need to develop the full decision tree. But here in AdaBoost we need to just construct the stump. That means we need to construct we need to find out the root of the tree, and directly we will assign the leaves. Okay, so the stump construction, that means we need to construct the stump. Then how can we find out the stump? That means how can we find out the root of our stump? And for that we can see here outlook, temperature, humidity, and wind. 4 features are there, and out of these 4 features we have to consider just one stump here. Okay, one feature here. Then which feature we need to consider? As already we discussed in random forest, that means we need to find out the most discriminative feature or most important features, the feature that has the highest discriminative capability. And for that we will use some of the information theoretic construct. That is, we need to find out the Gini impurity of each and every splitter. So that means the reduction of impurity by outlook. We need to find out the reduction of impurity by temperature, and reduction of impurity by humidity, and reduction of impurity by wind. One thing I need to mention here, in our random forest, we have to we have the flexibility to take the subset of features. But here in AdaBoost, we have to utilize all the features, no subset. Okay, so that means we have to consider all the features here. To find out the reduction of impurity by outlook, reduction of impurity by temperature, humidity, and wind, we will apply the same method that we have discussed in our random forest lecture. So it means at first we have to consider this data set, and this data set we have to think about, like, how can we know the impurity of this data set, or you can say impurity of the play tennis feature. Okay. So in this case, we can see how many yes and how many no. We need to find out that. So So for this data set, we can see 1, 2, there is no, here is one no, and another no is there. So no is 1, 2, 3, 4, and 5. So out of the 14, 5 no, and the rest of the elements are just yes. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 positives. So that means in our data set we have 9 positives, maybe 2, 3, 4, 5, 6, 7, 8, and 9. 9 positives and 5 negatives also. So we have 5 negatives, 3, 4, and 5. 5 negatives. So we have this data set, and we can say this is our D. If we consider this one is our D, then what we have to do, if this one is our D, we need to find out the Gini impurity of this. The Gini impurity of this set, it will be 1 minus probability of positive. What's the probability of positive? 9 by 14. So 9 by 14, probability positive, that is a square of that, plus then 5 by 14, 5 by 14, and a square of that. Okay. So what will be the Gini? On that case, the Gini will be 1 minus, Gini will be 1 minus 9 square divided by 14 square. Okay. So that means so it will be 56 maybe 196. So here um, it is 1 minus 9 square, that is 81, divided by 196, plus 5 square, that is 25, divided by 196. So in this case, we can see it will be 1 minus, so it is 6, and then 10, divided by 196. So it means it is 196 minus of 106, divided by 196. It means 90 by 196. So 90 by 196, 90 by 196 equal 0.459. So it is 0.459. So this is the impurity of our data set. So this is 0.459. Okay, now we have to think about if we use the outlook, then what will be the reduction? That means we have to find out that the reduction for outlook. Reduction for outlook. So we know that outlook, here we can say it can be sunny, it can be rain, it can be overcast. So outlook, just for the sunny, for the rain, and for the overcast. Okay. So for the sunny, outlook sunny, you can see here sunny 2, Here is also sunny. Here is the sunny. Sunny. How many times? 1, 2, 3, 4, 5. So 5 times sunny is there. So 5 times sunny, total 5 times. And out of the 5 times, how many times we made the yes decisions and how many times we made the no decisions? Here we can see for the this case sunny, we made the no decision. And for this sunny, we made the no decision. And for this sunny, we also made the no decision. And for this sunny, this is yes decision we made previously. And for this sunny, we made the yes decisions. It means we have 3 no decisions and just 2 yes decisions. So we can say we have a data set. This is called D1. This is the subset of D, where we have 3 negatives and 2 positives. Okay, 2 positive. So this is our D1. Now we have to think about our rain. So here the next type of outlook. It is rain. So this is rain, another rain, 3 rain, 4 rain, and 5 times we observe the rain. So for the 5 times rain, now we have to think about for this rain, what will be the prediction for this rain? Previously, we played tennis on that day. Okay, so yes, for this rain, here is also yes. And for this rain, there is no. Okay, and for another rain here, it is yes. So that means 3 yes, 1 no. For this rain, another no is there. So that means 3 positive and 2 negatives. So for the case of the sunny, we have a subset, and on the subset we have 3 positives, 1 positive, 2 positive, 3 positive, and 2 negatives. Okay, 2 negatives are there. So this is our data set D2. And now we have to think about, that is another one, outlook equal overcast. So if we outlook equal overcast, here is also overcast, here is overcast, and here is overcast. That means we can see 4 overcasts are there. And for this overcast, the decision here is yes. And for this overcast, decision here is also yes. And for this overcast, decision is also yes. And for this overcast, the decision is yes. That means all the 4 times we made just the yes decision. So for the case of our overcast, we all the time we have the same decisions. Okay, that is the yes decisions we made previously. Okay, so for the overcast, we have a set for the overcast, and that is positive, 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 and positive. So this is our D3. Okay, D3. That means outlook. If we use outlook as a splitter, then it will divide our dataset into 3 subsets: D1, D2, and D3. Now we have to find out the Gini impurity of D1 and Gini impurity of D2 and Gini impurity of D3. We can see that D3, Gini impurity of D3 is 0 because we can see all these are just positive. So that means this is a pure set. So we can say this is 0. And how about the D1 and D2? It is 1 minus, for the D1, it is 3 by how many? 5. 3 by 5 whole square plus of 2 by 5. That means probability of negative square and probability of positive square. So if we do the math, then we will get 1 minus 3 times 3 is 9. out of 5 is 25, and 2, that means 4 and 25, 4 by 25. So here we can see 1 minus 9, 4, this is 13 by 25. So finally we will get what? We will get 12 by 25. Okay, 12 by 25. So 12 by 25, it is 12 divided by 25 equal 0.48. So we will get 0.4 and 8. Okay, 0.48. So now we can see that is for this data set, for this D1, we will get the that is the Gini impurity 0.48. 0.48. So we can write it here 0. This is okay. The Gini impurity will be 0.48. Okay, 0.4. Now we have to find out the Gini impurity of another set, that is the D2. How can we find out the Gini impurity of D2? So in this case, we can see there is 3 positive and 2 negative. So it will be the same, actually 1 minus 3 by 5 whole square plus 2 by 5 whole square. So it will be the same. That is, we can write it like the instance for this one, Gini impurity will be 0.48 also. 0.48. Okay. Now we know that Gini impurity of D1 and Gini impurity of D2 and Gini impurity of D3. Now what we have to do, we have to find out the induced Gini by outlook. Okay, and we know how to do that. Induced Gini by outlook. So induced Gini by outlook, how can we find out that? So for the induced Gini, it will be Gini induced by outlook utilizing our dataset D. So it will be the cardinality of D1. So that means we got the 3 subset D1, D2, and D3. Then the cardinality of D1, how many instances in D1 we have? You can see 5 instances. Okay, there is 2 positives, 3 negatives. So total 5 instances in D1. And how many in D? We have total 14 instances in D. So this is the 5 by 14 times the Gini impurity of D1. It is 0.48. 0.48 plus of then Gini impurity of D2, it is 0.48, but how many elements in D2? We have the same, that is the 5 elements out of the 14, and then times Gini impurity of D2 is 0.48 also, 0.48 plus the Gini impurity of D3, and how many elements in D3? There is 4 elements in D3 out of the 14, and the Gini impurity of D3 is 0. Okay, so here is 0. If we do the math, then it will be
0.34.
0.34. Okay, 0.34. Okay, thank you. 0.34. Okay. So that means induced Gini by outlook, it is 0.34. Now we have to find out the reduction of impurity by outlook. So reduction by outlook. Okay, reduction by outlook, it will be it will be reduction of outlook. It will be so our Gini of the original data set, it was 0.459, 0.459 minus, if we split using the outlook, then induced Gini will be 0.34. Induced Gini will be 0.34. And the reduction will be 0.459 minus of 0.34 equal
0.119.
0.119. Okay, so this will be the reduction. So here we can write it here like 0.119. So this will be the reduction of impurity if we apply outlook to split our data set. Okay, so that means if we apply the outlook feature, then the reduction of impurity will be 0.119. Now what we have to do, we have to think about another feature like the temperature feature this time. Okay, temperature feature. We have to think about the temperature feature. So temperature feature. Temperature feature. And we can see temperature, it can be hot, it can be cool, it can be mild, 3 types. Okay, like the same thing, like outlook, we will get 3 subset, D1, D2, and D3 for the temperature also. Okay, for the temperature also. And similarly, we have to find out the Gini impurity of D1, Gini impurity of D2, and Gini impurity of D3. And then again, we have to find out the Gini induced by the temperature using the same kind of formula. And then we have to find out the reduction by outlook. Okay, so similarly we have to do that. That's why I think I have already calculated those things for you. No need to show, I think, in details, as I have already shown the outlook. For the case of the outlook, you can see 0.343, that is induced Gini, and that's why the reduction we have already computed. Reduction, it is 0.059, 0.459 minus 0.0 it is 0.3, then 4.3. Okay, and we have already computed this one is 0.119. Okay, so that's what we have written here. Reduction is 0.119. So if we consider the temperature, then you will get the same thing like here. For the temperature, the induced Gini you will get 0.441. Okay, so you will get induced Gini 0.441. The reduction by temperature will be reduction by temperature. It will be 0.459 minus 0.441. What's the value?
0.018.
0.018. Okay, so this will be the reduction if we apply temperature to split our data set. Okay, we need to note it, that is 0.018. Similarly, if we apply the humidity, then the induced Gini will get 0.367. Okay, 0.367. Then the reduction you will get reduction by humidity. Okay, reduction by humidity. So you will get 0.05, sorry, 0.459, 0.459 9 minus of 0.367. 367.
0.092.
0.092. Okay. So we'll get 0.092. So this is the reduction by humidity. Now we have last one, that is we have 4 features. So last feature is wind. So if we apply the wind, then induced Gini, you will get 0.429. So this one, 429. Then reduction by wind, it will be 0.459 minus of 0.429.
0.03.
0.03. Okay. 0.03. So now we have calculated, that is there is a reduction of impurity by wind, reduction of impurity by humidity, reduction of impurity by temperature, and reduction of impurity by outlook. Okay, and we already now we have to compare the reductions. Okay? The reductions also called the gain. The gain. Okay, so that's why the gain, the higher the gain is better, or you can say highest the reduction is also better. So here we can see now the gain or more reduction for outlook, it is 0.119. If we compare 119, then 0.018, and then 0.092, and then 0.03. Okay, so that means the highest reduction we got from outlook, reduction from the outlook. Okay, outlook. So that is the gain, highest gain we got from our outlook. So this is the highest reduction. Highest reduction. It means that we have to construct the stump starting with outlook. That means that in our parent node of our stump, we have to consider outlook. Yeah, outlook we have to consider. Here we can see that is the outlook we have. We have considered the outlook. Okay. Now the outlook, you can see in our data set the outlook 3 types. Okay, 3 types, like outlook can be sunny, rain, and overcast. So that's why we have written like outlook can be sunny, it can be rain, and it can be overcast. Now now we have to think about, that is the, if outlook equal overcast, then what will be the answer. Okay, if outlook equal overcast, from our data set, specifically from this part, you can see for the outlook, this is the splitter is there. So for the outlook splitter, so this is splitter, sunny, rain, and overcast. And for the overcast, we can see for this overcast, all the times we made the positive decisions, that is 4 positives are there. In D3, we have all the positives element. Okay, so that means when outlook equal overcast, all the elements are the positive. Okay, so that's why we can say that at this stage we can make the concrete decision if outlook equal overcast. It means that if outlook equal overcast, all the time we played the tennis match. So no need to think about other parameters or other things. All the time we will just the decision will be just the positive. Okay, so that's why in our decision, the stump construction, we will use, if outlook equal overcast, then we will use here yes. Okay, that means all the time positive decisions. Now we have to think about outlook equals sunny. What will be the decision if outlook equals sunny? And we can see that If outlook equals sunny, for this case, outlook equals sunny, we got 3 times positive, 3 times negative decision and 2 times positive decision. We made 3 times positive, 3 times negative decision and 2 times positive decision. That means those are mixed up decisions. So if those are mixed up decisions, that means we cannot directly say that yes and no at this case. We cannot say yes or maybe no. We cannot say at this stage. So what we can usually we can do, we have to think about like maybe some other parameters, okay, to make the final decision. But the problem is, in case of our AdaBoost, we have to consider this stump, and a stump it will have just only one node at the parent, and the others will be the leaf nodes, okay. Other will be just leaves. So that's why at this stage we must make the decision, yes and no decision. For that, what we have to do, we have to think about like probabilistic decision at this case, the probabilistic decision. The probability of yes and probability of no, which one has the highest probability? Like in this case, 3 positives and 2 negatives, 3 negatives and 2 positives. The probability of negative is greater than the probability of positive. That means we can say probability of negative here is 3 out of 5. Okay? And probability of positive here is 2 out of 5. 2 out of 5. So in that case, we can see the probability of negative is high. So that means in that case, we have to make the probabilistic decision. And that's why if outlook equals sunny, you have to say no, we will not play tennis. Okay. Similarly, for our outlook equal rain, on that case, outlook equal rain, on that case, we can see we have 3 positives and 2 negatives. That means mixed up decisions are there. So again, based on the probability, that is, we can see that probability of positive is higher than the probability of negative in case of outlook equal rain. So that means on that case, we have to say if outlook equal rain, then it will be yes, because probability of yes or probability of positive is higher than the probability of negative. Okay. So probability of so that's the finally we will get this stump. So this is our stump 1. STUMP stump 1. Okay. So this is how we have to construct that stump. If we go back to our algorithm, you can see fit classifier. That means we have to develop one classifier, that is develop one stump, and that is G1. And then what we have to do, we have to pass our data set to the G1, and it will produce the output either -1 or maybe +1. Okay. So now if we can think about our, that is if we pass our data set to the step, our data set, this is our data set. We pass this data set to our step. I have to clean it, maybe discuss it further. Okay, now we have to pass this data set to our stump. So it means so this is our data set, and we have to pass it to the stump, that is constructed stump. So this is our stump. Then if we pass this one here, then what will be the output from the stump? Why I cannot make it? Okay. Okay. Now pass the first instance. First instance, that is day one, to the stump. So in our case, that is the day one. We can see if we pass this instance, that is the X feature here. So these features to our stump here. So if we pass it here to this stump, then we can see at first it will check the outlook. Okay, outlook. So here is also, in this case, we have the outlook, and we can see outlook in case of our first data, that is day1 data, the outlook is sunny. So outlook is sunny. Okay, outlook is sunny. So this is outlook is sunny. So now we can see if outlook is sunny, then the decision here we can see it is sunny. That means no. Okay, the decision is no. If outlook is sunny, then decision is no. So we have to write here there is no. This is our no. That is n. N is no. Okay. Okay. No. Then we have to pass the second instance. That is day two. The instance here, the day two, second instance, and then the x value. That means the feature values. So here the feature values. We have to pass those feature value here in the stamp. And again, what it will check? It will check the outlook. That means the outlook we have. It will check the outlook. And outlook equal what? Outlook equals sunny in this case also. So sunny. If outlook equals sunny, then we have to move in this direction, and again we will get no. So if outlook equals sunny, and again we will get no here. Okay, so that means we will get no here. Previously we got the no, and this time also no. We have to pass the third instance. So now we can see it will check the outlook, and outlook is overcast this time. Outlook is overcast. So if outlook is overcast, the stump will return what? It will return, if outlook is overcast, it will return yes. Okay, it will return the yes. So that means for the overcast, it will return yes. That means y. Similarly, we have to pass the day 4. Then if we pass the day 4 here, there is day 4 again, it will check the outlook, and day 4 outlook is rain. The rain. And if rain, then we can see it will move to this direction, and that means we can see the yes will be the output from stump 1. So that means for the rain, the output will be yes. Okay, output will be yes. For the day 5, now we have to pass again, and it will check the outlook. Outlook equal rain, and rain is yes. So that means rain is yes. And then we have to pass the day 6. Outlook equal rain, and rain, here it will pass the rain, and rain is yes. Okay, so rain is yes. Again, we have to write the yes. Then we have to pass the day 7, and it is overcast. And you can see overcast is also yes from this stump. Overcast is also yes from the constructed stump. Then we have to pass day 8, and you can see day 8 is sunny in that case. So for the sunny, the stamp will return sunny is no. The stamp will return stamp will return no here. And then day 9, the sunny, and stamp will return no. So here is no. And then we have to pass the day 10. Day 10 is rain, and rain is yes from our stamp 1. It is yes. And then day 11 we have to pass. Then we can see day 11, and here is the sunny, and day 11 sunny is no. So here is no. And then day 12 is overcast. Overcast is yes. From the stamp 1 we got yes. And 13 is overcast, and overcast we will get yes. And from rain, that is day 14, it is rain, and rain, you can see the rain is yes. Rain is yes. Okay, so that means we build our stump and then feed our data to the stump, and it will return either yes or no. That means negative or positive. So we have uh, already discussed that is how many positives and how many negatives we got. Now what we have to do according to our algorithm, we can see that is we have to compute the error. So error we have to compute. In our previous class, I have discussed this one, the unit function and all these things. You can see the error, how to compute the error. Error for m, error m is 1. That is error for the first stem. It will be the summation of the weights of the misclassified instances. And this misclassified, it will be identified by this unit function. The misclassified. Now, from our data set, we need to find out the misclassified instances. So misclassified means the original annotation is different from the stamp's output. So we can see that is for the first output, first day, original output is no, and stamp also say no. Okay, so n and no. That means this is correct. And then second one, original is no, and stamp also mentioned no. So correct one. Third is yes and yes. Fourth is yes and yes. 5 is yes and yes. So correct classification. 6 is yes. Originally no, but our stamp mentioned that the answer should be yes. Okay, so that means this is a misclassification. So this is a misclassification. And day 7, yes and yes. So correct classification. Day 8, no and no, correct classification. And the day 9, you can see originally yes, but our model mentioned that it is no. Okay, so here is another. This is another misclassification. Day 9. Day 10 yes and yes, correctly classified. Day 11 yes and no, so this is a misclassification. Now day 12 is yes and yes, that is same. Day 13 is yes and yes, also same. And then day 14 is yes and no, that means different. So this is a misclassification. Okay, so it's a misclassification. So that means we can see that we have 4 misclassified instances. So according to our algorithm, what we have to do, we have to sum up. We have to sum up the weights of the misclassified instances only. Okay, and divided by the weights of all the instances. So weight of the summation of the weights of all instances, it will be 1. The first time it will be 1. So that means we have to the denominator will be 1, and in numerator we will just summation of all the weights. The summation of all the weights, that means you can see in our data set, these are the weights, and how many instances are misclassified? That is 4 instances. The weights of each and every instance are the same. Okay, so 4 instances means the error will be 4 times 1 by 14. 1 by 14. So 4 times 1 by 14. That will be the error. So then if we calculate the error, the total error, 2 times 1 by 4 and 2 times 1 by 4, that is 4 times 1 by 4. You'll get 2 by 7 and you will get 0.29. Okay, 0.29. So that will be our error. That means according to our algorithm, here ERR of 1, here ERR, that is error of 1 will be 0. 0 point hot, 0 point here 0.29. Okay, 0.29, 0.29. Okay, this will be the error. Now the next step, it is compute the alpha value. Okay, alpha means amount of say or weight of the vote of different systems. Then we have to use this error to find out the weight of the vote. So this error here in this equation. So actually it is like log one minus error. Error of 1 is 0.69. Sorry, 0.29. 0.29. 1 minus error divided by the error 0.29. 0.29. Then we have to the log of this. Okay. So if we find out that, then the alpha value we have already calculated here. The alpha amount of say you will get 0.45. So that means alpha of 1 it is 0.45. 0.45. So 0.45 is the weight of the vote. Weight of the vote of our fast system. So you already got the weight of the vote of our fast system is 0.49. Okay, 49. This is also called the amount of say. Amount of say of our system. It is 0.45. 0.45. Now we can see that according to our algorithm, After computation of the alpha, that is the amount of say, we have to update the weights of misclassified instances. Okay, misclassified instances by the factor, we can see W equal W times e to the power alpha. So this equation, using this equation, and we have to update these weights for misclassified instance for I equal 1 to n. Update the weights of misclassified instances. Okay, so it means the weight we need to update, the new sample weight would be, that means W will be the previous weight is W times e to the power alpha. We know that the weight of misclassified instances, all the cases, it is 1 by 14 times e to the power alpha is what? Alpha is 0.45. 0.45. So that means using this equation, we can find out the new weight for the misclassified instances. Okay, so incorrectly classified or misclassified instances. Sample weight times e to the power alpha. It will be 0.1. 0.1. We need to update the weight of misclassified instances using the factor e to the power alpha. Similarly, we have to decrease the weights of incorrectly or correctly classified samples. That means classified samples, we have to decrease the weights. And the factor is the same 1 by 5 e to the power, but this time negative alpha. So this time negative alpha. So we have to decrease the weights of correctly classified samples, and that is 0.046. Okay, so this one 0.046. And now we have to update the weight. We can see that is, this is our data set, and the sample weight previously we have the equal weight for all the instances, like 1 by 14, 1 by 14, 1 by 14. But this time we can see that is for each and every instance, the weights are different. For the correctly classified instances, the weights are 0.046, and misclassified instances weights, we have to assign 0.11. So we can see from here that is the day 6. So the day 6, this is one of the day 6. The day 6 is misclassified. The weight of that misclassified instances, it will be 0.11. There is also another misclassified instance, which will be 0.11. And here another misclassified instance, 0.1. And another one here, it is also 0.1. And how about the others? There is the weights of other instances, it will be 0.046. Okay, 0.046. That is this weight. For other instances, weight will be 0.046. So here, other instances like this, the weight of this one, it will be 0.046. For next one, 0.046. So in this way, we have to assign the weights of other instances also. Okay. The sample weight, new sample weight, updated sample weight. So any question up to this point? Do you have any confusion? Any question? So it means no question from your side. So now what we have to do, that is, we have to think about our construction of our next stump. Okay, next stump. And in our last lecture, we have already discussed that is next stump we have to construct it from the output of our first stump, considering the output of our first stump. So that's why what we have to do, we have to form a new data set for the second stump. We have to form a new data set for the second stump. And how can we form the new data set? To form the new data set, at first what we have to do, we have to normalize the sample weights. Okay, so these are the sample weights. We have to normalize it. So you can apply any normalization approach, but here the normalization approach is given is we have to sum up all these values, all these sample weights. We have to sum up all these values. So that means it will be the sum, let's say sum of weight, sum W. So that is sum of the weights of all the samples, of all the samples. So that is the sample weight. Now what we have to do to find out the normalized values, the sample weight, that is each and every sample weight like this one, we have to divide by the summation. So like here is 0.046 divided by the summation. Then you will get the value like 0.051. So you will get 0.05051. Similarly, we have to the next, that is this value, we have to divide by sum W, and you will get again 0.051. So here is the 0.051. But this one, that is the 0.11, 0.11. So we have to divide 0.11 by sum W. Sum of the weights. So on that case, if we divide 0.11 by the sum of the weights, we will get 0.122. 1, 2, and 2. For this one, you can see 0.122. For this one, it is 0.122. For this one, it is 0.122. For this one is also 1.122. Okay, so 0.122. So this is called the normalized sample weight. Normalized sample weight. And then what we have to do, we have to find out the cumulative normalized sample weight. So cumulative normalized sample weight. It means the running sum we have to determine. The first one is the first one is as it is 0.051. But the next one, this one, it will be the summation of the first two. Next one. The next one will be the summation of first three. Then the next one will be the summation of these four. These four. And you will get 0.204. And then the next one will be the summation of this 5. It is 0.255. Like this way, we have to calculate the cumulative normalized sample weight. That is called running sum. Okay, so you will get the cumulative values here. Anyone has any question here? I think no question. These are very easy things. Okay, now what we have to do, the next thing is uh, we got the cumulative normalized sample weight. Here is the cumulative normalized sample weight. We got these values. Previous last step. Okay, cumulative normalized sample weight. And now what we have to do, we have to generate the random numbers within 0 to 1, 14 random numbers. Because we have 14 instances in our data set, and we will generate 14 just random number, okay, within 0 to 1, the value within 0 to 1. Within this duration, we will generate 14 random numbers. Okay, then I have generated here that this is the list, and it will be different from you. Maybe if each and everyone has to generate the random numbers, and maybe we will think about that is the random numbers as we think at that moment. Like maybe the one random number generated, I have generated is 0.7, then 0.2, 0.3, 0.6, 0.04, 0.5, like this way. Okay, that means on that moment, whatever in my mind, the numbers, I can maybe just consider those are our generated random numbers. That is, I have to generate 14 random numbers. Okay, now after generation of the 14 random numbers, what we have to do, for each and every random number, I have to find out the interval in our cumulative normalized sample weight. Let's say the 0.7, this one, our generated random numbers. So what I have to do, I have to find out the 0.7 belongs to which interval of our cumulative normalized sample weight. The 0.7. So we can see this is 0.2, 0.3, 0.4, 0.6, 0.6, 0.7. Okay. So that means if we consider this interval, then 0.7 will be 0.7 will belongs to that interval. 0.652 and 0.774. So within this boundary, we will get just 0.700. Okay. So we have to find out this interval. So we already find out this interval. And then after finding out the interval, we have to find out the upper bound of that. The upper bound of this interval. So upper bound is 0.774. 0.774. This is the upper bound of that interval. And then we have to copy the instance belongs to the upper bound of the interval. So that means we have to copy this one. There is upper bound. The instance belongs to the upper bound. The upper bound belongs to that instance. Okay. So we have to copy the 11 and paste it in a new data set. We can see the 11. Okay? The 11. This is the day 11. We have pasted here. Copied from there and pasted here. Similarly, we have to take another random number. Maybe you can say 0.250 and find out the interval here. 0.250. Here is the 2 and here is the 255. That means within this interval, we will get this value. So that means this is the interval. Then we have to find out the upper bound. So upper bound is this one. This one is the upper bound, 0.255. This one is the upper bound. And then we have to consider the instance belongs to that upper bound. So that means you can see we have to consider this instance, copy this one, and paste it to our new data set. So day 5, you can see here is the day. Pasted here. Similarly, we have to take another one, maybe this one, 0.886. And you can see the 0.88, that means it will be within this range, within this interval. So we got that, and then find out the upper bound. So this is the upper bound. And the instance here, we can see this is the instance that belongs to the upper bound. So we have to copy this one. We have to copy this one and paste. That is day 14. We have to paste it here. We have to day 14. In this way, for the all the generated random numbers, we have to find out the interval in our cumulative normalized sampleoid, and then select the upper bound, and then select the instance that belongs to that upper bound. And we have to copy that in our new dataset. So that means we will get the new dataset like this way, in this new dataset. This is our new dataset. And in our new dataset, we will also have the 14 instances, 14 instances, because the 14 random numbers we have generated. And for each and every random number, we will get just one instance in our new dataset. But in our new dataset, the properties, if you can check the properties of that, then you will find that some of the instances are not copied from our original dataset. Some of the instances are not copied. Like you can see 1, 2, 3, 4, 5, 6. Instance number 7. Instance number 7 is not copied from this original dataset to our new dataset. Similarly, maybe instance number 8 is also not there. Okay, that means 8 is also not copied from the original dataset to the new dataset. But if we closely observe that, some of the instances are copied also multiple times. Some of the instances are copied multiple times. Like in this case, if you can see, you can say day 14. Here the day 14 is copied. Here the day 14 is copied. Here is the day 14 is copied. It means day 14, that instance appeared multiple times. Similarly, maybe some other instances also can appear multiple times, like day 11 multiple times. Here is also day 11. Day 9 also. Here is the day 9. The day 9. Okay, some of the instances are copied multiple times. So now this is our new data set. And considering this data set, we have to again try to construct our second storm. So we need to consider this data set and then try to construct our second stem from this data set. And for that, again, we have to initialize each and every instance's value as 1 by capital N. And here is also 1 by 14, 1 by 41. So we have assigned those values for the instances. Okay, so using this data set, maybe we will get another stamp. Previously, we got like one stamp is Outlook. So this was the stamp 1. And using this data set, we will maybe get another stamp like this. On that stamp, we will get maybe humidity. Okay, humidity may be normal and high. So for the case of the high and for the case of the normal, maybe we can assume that, okay, this is our stem 2, and for the normal, maybe we will play tennis, and for the high, maybe we will not play tennis. Okay, so just I didn't compute uh, to find out the stem. Assume that this will be another stem. This is just an assumption. So actually, we have to again find out the reduction of impurity by outlook, reduction of impurity by temperature, reduction of impurity by humidity, reduction of impurity by wind, and then we will find out that is which one has the highest reduction or highest gain, and that one we have to place at the root of our second stem. Okay, and then we have to check that is the yes and no condition, what is true and what is false, and then based on that, the humidity is normal, you will get yes, and humidity is high, maybe no, like this way. So this is just I assume that you will get this one. So this one is also I left as your homework. Okay, so you can, this one is a homework, and this time no need to submit the homework, but again you can do it for the practice. Okay, for the practice. So construct the second stem, and then apply the procedure, the same procedure again to find out our again the new data set for the third stem, and in this way maybe you can construct many stems. But the question here is in this new data set, it is mentioned that we need to pay more attention to the misclassified instances. As in our theory we have discussed, that is, for second stem construction, we need to think about, that is, we need to pay more attention to the misclassified instances. But how we paid more attention to the misclassified instances here? We can see that, and that is the misclassified instances for our case is day 6 is misclassified, one of the misclassified instances, and day 9 is also one of the misclassified instances, and day 11 is also misclassified instances, and day 14 are also in misclassified instances. So those 4 are misclassified instances. And if we closely observe our new data set, we can see the day 6, this is day 6, here is the day 6, and this is day 9, here is the day 9, this is day 11, here is also day 11, and day 14 is there, here is also day 14, here is also day 14. That means the misclassified instances appeared multiple times in our new data set. So to pay more attention to the misclassified instances, this is the trick. Specifically, we will consider more instances of misclassified instances. So that is how we paid more attention to the misclassified instances, so that maybe it will be correctly classified in next stem. But how actually it is ensured that those misclassified instances will appear multiple times in new data set? Because we just generate some random numbers here. Okay, generate the random numbers here. How the generated random numbers will ensure? Specifically, the generated random numbers and cumulative weighted sample. The cooperation between these two ensure there is the more instances will be the misclassified instances will be copied more times in our new data set. How? Because we can see there is the interval of our misclassified instances. So this is the interval of our misclassified instances, and this is the interval of our misclassified instances, and this is another interval of misclassified instances, and this is another instances of misclassified instances. The range between these two, we can see if we subtract, then it is the uh, difference. It is 5 and 7. That means 0.122. The range between these two is also the same, 0.122. And range between these two is also the same, 0.122. And here is also 0.122. But if we think about just any other pairs, okay, other pairs, like maybe we can say these two. If we consider these two, there is no misclassified instances in this pair. So the difference between the length between these two, it is 0.051. Here is also the same. If we consider these two, the range will be 0.051. Okay, if we consider these two, and then we will get again, it will also be 0.051. So it means the range of misclassified instances, this range between these two numbers, those are higher. So that means 1 to 2, this is higher than the range of misclassified instances. Those are higher than the correctly classified instances, 0.51. So this is this range is higher than this one. If we generate the random number, then we will generate the more random numbers on the highest, that is the highest interval. So this interval is higher than this one. So if we generate the random numbers, then within this interval, we will usually generate more random. We will usually generate more random numbers for that case. So that means if more random numbers are generated within those duration or within those range, then it means more that is the misclassified instances will copied more times. Okay, so this is how the generated random number and cumulative normalized sample weight ensure that the misclassified instances will copied more times in our new data set. Okay, new data set. So it means the misclassified instances are more than the correctly classified instances. So we paid more attention to our misclassified instances for next level STEM generation or next level classifier. So this is in this way, maybe we will construct the STEM number 3, then maybe STEM number 4, STEM number 5, like this way. Okay? So now the last thing is how the bagging is performed in our AdaBoost classifier. So in random forest, we already discussed the bagging procedure for the random forest, but how in AdaBoost the bagging will perform to generate the final answer, okay, final answer or final class. So let's say we have one query like day 30, the outlook, is sunny maybe, and then the temperature temperature, maybe cool, and the humidity is high, and then wind is strong. Then what will be the Platonist decision, the predicted Platonist decision for that case? Then what we have to do, we have to pass this query to stamp 1, stamp 2, and stamp 2. That means all the constructed stamps. Let's say this is the stamp 1, ST1. We have already constructed it. The outlook overcast is yes. Outlook rain is also yes. Sunny is no. And then humidity normal is yes, and maybe high is no. And maybe we have another stamp like temperature. So temperature hot, mild, and cool. Okay, hot, mild, and cool. Now, for the hot, maybe you can say no. That is for the mild and cool, maybe yes and yes, like this. Okay, so consider that we have these three stamps: stamp 1, stamp 2, and stamp 3. So this is our stamp 3, and this is our stamp 2, stamp 2. And we know that is in construction of the stamp, we also know that the weight of the vote of each and every stamp, or amount of say, that is the alpha value. So we have determined the alpha for our this system, stamp 1, that was 0.45, if we can remember that. And let's say there is another stamp, we have the humidity, and the alpha for this is 0.23. And for temperature, the alpha is 0.56. Just assume those, because we didn't construct. Okay, so actually you can construct and find out the actual value of alpha. And now what we have to do, from our stamp 1, stamp 2, and stamp 3, and 3 stamp, and there is the two outputs. One is yes, and another output is no. Okay, so we have two outputs, yes and no. Now if we pass this query to our stamp 1, and then it will check the outlook. And we can say that the outlook is sunny. So if outlook is sunny, then the answer will be no. Okay, answer will be no. So that means on that case, stamp 1, it is mentioned the no. So no, so it will count the vote that is equal to the amount of say, that is the weight of the vote. So it will count the vote that is 0.45. So on that case, for the stamp 1, the no will get the vote, but for that case, the no, it will get the weight of the vote will be the 0.45. Okay, 0.45. Then we have to pass the same query to stamp 2. So here is stamp 2, and we can see there is the it will check the humidity. So humidity is high. If humidity is high, then the answer is no again. So no. The no will get the port 0.23. Okay, so it will be 0.23. And then we have to pass the same query to our stamp number 3. It will check the temperature. We can see temperature is cool on that case. If temperature is cool, then the decision is yes. Okay, decision is yes. So stamp 3 will vote for yes. And what will be the weight of that vote? It will be 0.56. So that means here it will be 0.56. 0.56. Now we have to count the vote for yes and vote for no. And we can see vote for yes, the total vote for yes, it is 0.56. And total vote for no is 0.45 and 0.23. That is, it is 0.68. 0.68. If we compare the vote for yes and vote for no, that is 0.68 is greater than the 0.56. So this 0.68 is for no and 0.56 is for yes. So that means no will be the winner on that case. No will be the winner. So in such a case, the decision will be here no. Okay, so it will return the AdaBoost classifier will return the no. Okay, this is how the bagging approach of AdaBoost works. So that ends our today's lecture also. That is the AdaBoost classification. So if you have any question or queries. No question? Okay, so if you don't have any question, I think thanks for the joining this class. See you in your next class then.
Sir, will we have our class on 24th?
Yes, we have.
Okay. And
Okay,
31st, we have
you.
no class.
No, 31st, no class. It's the holiday and vacation we have.
Okay, sir. Thank you.
স্যার আমাদের এই কোর্সের কুইজ নিয়ে এখনো ডিসকাশন হয়নি, মানে এটা কি রেডি করতে হবে কুইজটা?
এটা মিড টার্মে পরে নেই, হ্যাঁ একটা কুইজ নিই তো
আচ্ছা, আচ্ছা।
সাধারণত মিড
জি,
টার্ম
স্যার।
পরে নিব।
আচ্ছা স্যার।
স্যার আমাদের একটাই কুইজ হবে।
হ্যাঁ একটাই কুইজ নিব আমি। সবাই প্রেজেন্ট থাকার চেষ্টা করো ওটাতে। আর যদি মানে কারো কুইজ হচ্ছে ভালো মার্কস না আসে তাহলে তাদেরকে আমি আবার হচ্ছে স্পেশাল কুইজ দেওয়ার হচ্ছে অপশন দিয়ে থাকি আর কি, হ্যাঁ সেই হিসাবে
জি স্যার।
একটাই কুইজ হবে আমাদের।
জি স্যার, থ্যাংক ইউ স্যার।
Okay, thanks everyone for joining. See you in our next class. Attendance সবার